Okay, so we're going to start now a topic that I think, or I hope that you will like, perhaps more than other topics, particularly because it may have a little bit of a GCSE feel to it, in that we're going to be using some formulas effectively, which I think some people quite like the idea that you just get numbers, you plug them into a formula. Having said that, you are still going to have to think about what it is you're doing. Don't just pick the wrong formulas. But yeah, at the end of this, we'll have learned two new formulas out of a set of four. There'll be two more coming next time. And these are going to help us with modeling and understanding situations, again, where we've got constant acceleration. So we're going to be making use of velocity time graphs to justify these formulas that we're going to look at. And then once we've justified them, we'll see how we can use them. Before we get into the formulas though and how we use them, first question here on the first slide, mainly just to check we've got an intuitive understanding of constant velocity and constant acceleration. So four scenarios there. A bowling ball dropped off the first floor of a building, a box pushed along the floor at constant speed, the Earth orbiting the Sun, and a leaf falling off a tree. All of those are describing some sort of motion. And then the question is, for each of those, well, two questions for each of those. Is there constant velocity? Yes or no? Is there constant acceleration? Yes or no? So see if you can quickly jot down, or in your head decide what you think the answer is for each of those four. And then once you're ready, I'll reveal the answer. So pause and have a think. Okay, so first one, bowling ball being dropped off the first floor of a building. Not constant velocity. Hopefully that makes intuitive sense. An object on Earth falling, especially a heavy object like a bowling ball, is going to be getting faster and faster and faster and faster. From a first floor building, it doesn't have time to reach what you may have heard of before as terminal velocity. If you're not quite sure what that is, then don't worry about it too much. But I've effectively said a first floor of a building, so that it ensures that we can rule that possibility out. Ultimately, any object falling in air, if given enough time, will reach a constant speed. But at such a short distance, and especially something heavy like a bowling ball, we're going to say air resistance not so much an issue. It's definitely just accelerating. So that's acceleration, and it is in fact constant acceleration. And therefore, if it's constant acceleration, greater than zero, not constant velocity. Okay. Number two, a box being pushed along the floor at a constant speed. Constant speed, therefore constant velocity, should make sense. The only thing is, as a technicality, this is also constant acceleration. If something's moving at constant velocity, it's also moving at constant acceleration of zero, right? Zero is a number. It's a constant number, or it's a constant. So if something's got a constant velocity, it's also got a constant acceleration. So we can have both there. The converse, of course, is not true. If you have constant acceleration, you may not have constant velocity. Okay, number three, the Earth orbiting the Sun. This one's a little bit of a tricky one. So let's draw, I'm going to draw a not to scale, not very accurate diagram. Bird's eye view, if you could have birds in space looking down. So you've got the Earth. It's going around the Sun. And let's simplify it for a moment and say, okay, it goes in a circle, for instance, and it feels like it's going at a constant speed. Yes, constant speed perhaps. You know, it's we see, from our perspective, we see the sun move through the sky. It's not getting faster or slower, so it might seem like a constant speed, but it's not a constant velocity, and This actually goes into something a bit more advanced, which is circular motion, which we don't need to learn about now. But I think the principle is within our understanding that at this stage it's going in that direction, whereas over here it's going, or trying to go, in that direction, the Earth. Point being, if you move in a circle, your direction is clearly changing, right? You're constantly changing direction. If you're changing direction, that must mean you're changing velocity, because velocity is both magnitude and direction. So the magnitude might be the same, that is to say, it's a constant speed, but it's not a constant velocity because you're changing direction. So in the same way, if you're running at a constant speed, but you're curving around a road, you may feel your speed is constant, but your velocity is not constant because you've changed direction. So I don't want to get into the full complexity of the question, but I do just want you to identify this idea that if your motion is changing direction, you can't have a constant velocity. So not constant velocity, but there is in fact a constant acceleration. Okay. Why it's constant acceleration is ultimately down to the fact that gravity provides a constant acceleration. In some sense, it's similar to part one. A bowling ball experiences constant acceleration. Likewise, the Earth experiences this force from the gravitational pull of the sun, which is also a constant acceleration. Okay, and then finally, a leaf falling off a tree. Getting into technicalities a bit, what is the distinction between number 1 and number 4? The main thing I wanted to draw your attention to is this concept of air resistance, which sometimes we tend to just ignore it, but in some scenarios it's not really realistic to ignore. So a bowling ball being thrown off a building, I would say the air resistance can largely be ignored for the purposes of calculating things like how long will it take to hit the ground, how fast will it be going. But a leaf falling off a tree, a leaf is, so light and has such large surface area, the air resistance is going to be a big deal. So for that one, I wouldn't just say it's a constant acceleration. In fact, I would say when it initially falls, it's probably neither. When the leaf first comes off the tree, it started at rest, and then it eventually reaches some sort of speed at which it starts falling and floating down. Eventually, it'll be traveling at constant velocity, but earlier on, it won't be traveling at constant velocity, and it won't be traveling at constant acceleration. I think it's probably a bit too much to get into now, but I think I'm just going to summarize and just say air resistance complicates things. Okay, so for that one, I'd say there's no simple answer. It depends on what you want to assume or what you can disregard in your model. So we won't see something that's actually that complicated for now. Okay, we'll mainly be looking at things like number 1 and maybe stuff like number 2. Okay, things where we've got a very obvious constant acceleration. Cool. All right, so hopefully that just clarifies in your mind these two concepts, and we can now take a look at how we get these formula. Okay, so there's 5 variables we're going to be using in these formula or formulae. They are commonly and will always be referred to in this context as S, U, V, A, and T. And therefore, because they spell out a word, when you put them in a certain order, we're probably going to be calling them Suvat equations. Technically, if you want to Google them or research about them, they're called the equations of motion. They're sort of the basic equations of motion, but within A-level courses and within the textbook, we're just going to call them Suvat equations by nature of the variables that are part of them, these 5 variables, S, U, V, A, T. And each of those stands for something. In some cases it's obvious why, in some less so. A is acceleration, makes sense. T is time, that makes sense. S is displacement. Much like in displacement time graphs, we use an S. Not entirely sure why, but that is what we're going to be using, S as displacement, potentially to distinguish it from D, meaning distance, I suppose. And then finally we've got U and V. So V is our final velocity, and then U comes just before V in the alphabet, and so therefore it has this connotation of occurring earlier. So U is our initial velocity, or the velocity that happened in the past in some sense. So when we talk about motion of objects, we tend to be interested in things like how fast was it initially going and how fast did it end up going. During that time, how much did it accelerate, how far did it go, how long did it take. All those questions I've just asked, there were about 5 questions in there, they correspond to these 5 variables. So what we'll do is we'll put these on a graph, on a velocity time graph, to start to see how we can come up with some relationships between the 5. Okay, so here's a generic velocity time graph. So there was some object which had this particular motion for some amount of time, and we can see how its velocity changed during that motion. So let's then remind ourselves, oh, we've got them here, right? These are the 5 variables, S, U, V, A, T. How are we going to mark these on this diagram? Where do they belong? So let's do U and V first. The initial velocity is here at time 0, and it's this value on the y-axis, right? That's our U. We tend to use lowercase. That's our U, and then likewise, if this is the end of the motion here, then it's again another value on the y-axis, which is our V here. Okay, so we're just marking the initial and final velocities. What about the time? So the time, well, if this here, that's times 0, so we get that for free. The initial time is always 0. You know, the time at which you started, we'll call that time 0. So then the time at which you finish, that's effectively your total time, right? So that's going to be T. Right? So it's the total time taken, or you know, the final time stamp at which you're considering is the final T, the end of the motion, where the start is 0, the end is T. Either interpretation, the T value is the same. So you've got T there marked, or you could equivalently just think of it as it's a distance of T, same thing. What's left then? UVT. Let's do A. What's A in this case? Well, if this is a velocity time graph, because this is a straight line, it's got a consistent gradient, a constant gradient. Therefore, the acceleration is just the gradient of this. Okay, so gradient of that line will be equal to A. Okay, and finally, S, which is total displacement, will be the area under this graph. The area equals S. Okay, so these 5 letters, these 5 variables, we've assigned them to various parts of the graph. Sometimes they're values on the axes, sometimes they're areas, sometimes they're gradients. But I hope you can see for this very generic, very basic motion of an object just accelerating from one velocity to another, we can label these 5 key values. Okay. And now what we can do is we can use this to derive some formulas. So we can come up with some relationships between these 5 letters. Let's see what we can come up with, right? So, for instance, we've got the gradient, right? The gradient of this line is A. So I know that. Let's consider gradient. The gradient's A, but can I express it another way without using the A? Well, gradient is just height, y difference divided by x difference, right? So what's the y difference? It's this height here that I'm moving along, which is the v value minus the u value, gives me that, right? So this distance here, this vertical height, that's v minus u. And then what about this horizontal distance? Well, that's just t, isn't it? We've got it down here. So in other words, a equals v minus u divided by t, right? And often what you'll see is this is the derivation of the conventional form of the formula. You tend not to see it written like this. You tend to see it slightly differently. Multiply both sides by t, you get this, and then add u to both sides, flip the equation, you end up with v equals u plus at. Same thing, right? All three of these are saying exactly the same thing, but it's this version that tends to be written as the standard formula. Okay, so we'll call this this is our first formula, okay, which is going to be important to us. It's if I have u, a and t, I can work out v. Or if I have v and a and t, I can work out u. So if I have any of those three, I can work out the fourth. Very useful formula. Okay, let's look at the second one then. What other things can I equate or relate to each other? Let's think about the area. So the area under the graph is S. But is there another way to express that? If we split this into two sections, this sort of trapezium shape, let's call them section A and section B, and let's note over here, so on the left hand side, B is very easy, right? It's the width is t and the height is u. So that height there is the letter u, so let's just call it tu. And then A is this triangle, which is half of that rectangle. That rectangle, again, it's v minus u multiplied this time by t and then divided by 2. So it's v minus u times t divided by 2. So let's add that all up. So b is ut, and then a is, let's expand the brackets actually. So we'll have a half of vt minus a half of ut. So then I've got ut minus a half ut, so that gives me just a half ut plus a half vt. And then finally I get, if I factorize that, I'll just have t times u plus v divided by 2. Okay, and that is again our standard conventional form. S equals u plus v over 2 times t, or t times u plus v over 2. Okay, that's our second formula. Okay, so from now on we're just going to remember those formulas and use them in our memorized form, but it's very important that you understand where they come from, right? They're just not magicked out of the air. We've done the explanation here throughout this slide, so if you ever, I mean, you shouldn't really be forgetting these formulas. You're going to be using them so much, but it's very good that if you can rederive it by just using this diagram. Okay, we've effectively proven these formulas in some sense by just considering a generic case and deriving them from the diagram. One very important thing, all of this again only works if we're using constant acceleration. So that's either 0 or a positive or a negative value, but it has to be constant. And why is that the case in terms of these formulas? Why does it matter? Because I assumed this line was straight. Okay, at no point have I actually considered the shape of this line. I've just assumed it was straight. If it was curved, then I couldn't have halved that rectangle area, and I couldn't have given this a gradient, a single gradient. It would have multiple gradients. So that's the fundamental assumption underlying everything you see in this picture, is that this line is straight, which is the same thing as saying the acceleration is constant. Okay, so please remember that everything we're doing right now only works if acceleration is constant. Okay, and then I'm not going to give you anything new here. I'm just really restating the formulas one more time, just because I want to clarify that they're so key. And I just want you to just look at them one more time now without the mess of all the working out on the previous slide. So that's our first, and this is our second. I'm calling them first and second. There's not really an order to these. So if you say to someone the second Suvat formula, that doesn't actually have any meaning. It's just the order in which we derived them. And I guess maybe one thing we can just point out here with this one, the second one, this is kind of intuitive anyway, even if you didn't have that graph, because in some sense, what is this thing here? It's almost like you can kind of think of it as an average velocity, right? Take your start and end velocity, divide by 2. Okay, again, only if you have constant acceleration. So it's kind of like saying, what's your average speed? How long were you doing it for? Multiply by time. That's your displacement, right? So it's quite an easy one to remember, I think. U plus V over 2 times t. Average velocity times time gives you distance. And then this one is also fairly intuitive, I think, in that it's saying you started with an initial velocity, u, and then add to that your acceleration times how long you were doing it for, and now you've got your new speed, your new velocity. That's all that one's saying really as well. So they're quite intuitive formulas, I think, these two. It would make sense why they would be the case. Right, so let's use them. So we're going to look at 3 examples. The first one's quite quick, and then you'll do some questions. A cyclist is travelling along a straight road, one-dimensional. She accelerates at a constant rate from a velocity of 4 to a velocity of 7.5 in 40 seconds. So I'm now going to start telling you your strategy for these. When you're seeing numbers, you should straight away just be writing down which variable that corresponds to. Turn the question into mathematics. So accelerates at a constant rate from a velocity of 4. So our initial u is 4, to a velocity of 7.5. So our final velocity is 7.5. And it took 40 seconds to do it, so t is 40. And then acceleration, I don't know, and displacement, I don't know. And in fact, I'm going to be asked what those are. So I also recommend doing this. Write down the missing variables and just put a little question mark or something. So then you've got your full Suvat sort of list with what you know and what you don't know. Find the distance she travels in these 40 seconds. So part A is basically saying, what is S? What's the magnitude of S, effectively, because it's distance rather than displacement. And then B is saying, what's the A? Okay, so then you just got to pick the relevant formula, right? So for part A, I want S, and I have U, V, and T. So I ask myself, which of those two formulas has S, U, V, and T, but not A? So it'll be this one, right? U plus V over 2 times T. And in this case, S is the subject, so it's already quite easy to do. So I'm going to do 4 plus 7.5 divided by 2 multiplied by 40. And if you work that out, you should get 230. And that's a distance, so it's 230 meters. And then part B, what's the acceleration? You probably guess we use the other formula. So we're going to write V equals U plus AT. And now in this case, A is not the subject, so let's make it the subject first. We get V minus U divided by T. That's what A is. Okay, and now let's put the numbers in. 7.5 minus u is 4 divided by t is 40. 7.5 minus 4 over 40 is 0.0875, and that's the acceleration of the object. So I've said the object, I guess we were talking about the cyclist this whole time. So the cyclist accelerated at 0.0875 meters per second squared, and the cyclist had a total displacement of 230, which is the same thing as distance in this case because it's a positive number. Okay, so let's see what's happening now. You'll notice it talks about particles a lot. That's just because it removes the need to worry about things like air resistance and stuff like that. A particle is ultimately just a tiny, tiny object. This particle then moves in a straight line from a point A to a point B with constant deceleration at 1.5. It's very important that we acknowledge it said the word deceleration here. We'll see how to deal with that in a moment. The velocity of the particle at A is 8 and the velocity of the particle at B is 2. Find the time taken for the particle to move from A to B, the distance from A to B. Okay, so let's do suvat. Let's write out suvat and put in the values we know and the ones we don't. The distance we don't know. The u is 8. That's how much it was at A. And then the v is 2. The deceleration is 1.5. So what that means is for acceleration for A, I'm going to put minus 1.5. And then t, again, we don't know. Okay. So for part A, we're going to use, let's see, I want t, but I only have v, u, and a, so I'm going to use v equals u plus at. And for part B, I want s, the distance, and I know u, v, and a. So again, let's pick the appropriate formula. In this case, it's going to be s equals u plus v over 2. And now I can say by t because I'm actually going to work out, I'm going to find t in part A, aren't I? So we have to do it in that order. We'll do part A and then do part B. Just to save us a bit of time, I don't think we need to actually work out the values. I think that explanation sort of speaks for itself. So for part A, you use that formula, plug in the values that you know, and then find what the value of t is. And then for part B, you'll put that value of t in here and put in u and v, substitute that into the equation as well, and you'll get your s. Okay, the arithmetic is itself not that complicated. Okay, the key thing is the method. So let's just write down the answers. If you do want to check that you're able to do that, you should be getting a t of 4, and you should be getting an s of 20. Okay. So then after reaching B, so this particle has gone from point A to point B, and now it continues to move to someplace point C. So it continues to move along the straight line with constant deceleration 1.5, so A hasn't changed. The particle is at the point C 6 seconds after passing through the point A. Find the velocity of the particle at C. I think at this stage we should draw a little bit of a diagram just to clarify what's going on here. So there was A, and there was C, and there was B. And then let's mark on the info. It's okay if we put more info than we need. So it was 8 here, meters a second, then it was 2 here. And C, we don't know how fast it's going. And we know that the distance from A to B is 20. and the time it took was 4 seconds. And then what's the new information we've got? After reaching B, same deceleration. So let's put above this whole time, double arrow to say acceleration, it's minus 1.5. And it's at the point C 6 seconds after passing through the point A. Okay, so that means from B to C, it must be 2 seconds, right? To give me a total of 6. Find the velocity of the particle at C and the distance. Okay, so the distance I still don't know. Okay, so we've got all the information there. So now let's create a new SUVAT, right? So a U, an S, a U, a V, an A, and a T, but it's for a different scenario. So the first one was from A to B. Okay, that's not real mathematical notation, that's just me noting. That's from A to B. And then this one is the B to C scenario. So different S's, U's, and so on. Okay, let's see what we get. So in that case, we've got T is 2, A is still minus 1.5, V I don't know, U is 2, because I'm talking about the scenario going from B to C, and S, again, I don't know. So 3 knowns and 2 unknowns, that's perfect. As long as you know 3 out of the 5 SUVAT variables, you should be able to find the rest. Okay. There'll be a couple of formulas to help us get some of them for scenarios we can't currently do, but that's our general rule which will be working once we know them all. 3 is enough. 3 out of 5 is plenty. So let's see if we can get it. Velocity of the particle. In that case, we're going to use again for part C. We're going to use V equals U plus AT. That will give me the velocity. And then for part D, we're going to use S equals U plus V over 2 times T. And again, you guys can plug the numbers in, see if you get the right value for C and for D. I'll just confirm with you now what those should be. You should be getting, for part C, a velocity of 1. And yeah, let's write that as V equals 1. And you should be getting a distance S for D of 21. And then on hindsight, I think actually I'm just going to clarify those answers a bit, because it's not quite as simple as just having plugged the numbers in. For C, that should actually be -1. So I grabbed these numbers from the textbook answers, but I think that should actually be -1. And the textbook has strangely just phrased it as a velocity of 1 in the reverse direction. But actually that will be a -1 velocity. What that's effectively saying is, if you can sort of follow my laser pointer, just watch what I'm doing, this is roughly what happened with the particle. It went like this. Oh, I think that's slowed down a bit. Let me try it one more time. So it's effectively gotten slower and slower and slower and slower and slower, and it's continued decelerating, and then it started reversing direction. So that's why we've got a -1 here, which makes sense. If you plug in the values, you should get V as -1. And that makes sense in that it's telling us it's now going at a speed of 1 meters per second to the left. The S being 21, really, that I should not just call S. The S value you'll actually get when you plug in T as -1, you plug in U and V and 2, you substitute that all in, I think you just get an S of, yeah, you just get an S of 1. So your S is 1, but your final answer, which is A to C, is going to be 21, because you've got the A to B distance, which is 20, and then from B to C, you've gone an S of 1. So you add that together, you get your final answer of 21. Okay, so don't just take it for granted like I did for a moment there that your S or your V or whatever are the actual answer you've been asked for, make sure you always reinterpret those values in terms of what you've actually been asked. So the distance from A to C for that part is not the same as my S here, because I have to add on that initial 20. Okay, cool. That example's done, I think. So with the time we've got left, let's try a few questions. I've got 3 slides of questions for you to try. Mainly just going to be using those formulas initially, and then the later questions you're going to have to perhaps do a little bit more algebra or some sort of problem solving. Okay, so start with pure calculation, just make sure you're using the formula correctly. Be aware of when things are positive and when they're negative. So for instance, I can spot here already for question 6, it says deceleration, so your A is going to be minus 1.2 rather than plus 1.2. Okay, so just be aware of those little things. That might be the main place you trip up if you're getting things wrong. So see how you do on these two. You can pause the video now. Okay, and then you've got a couple more to try here. There's one more question left, which is probably the trickier one. See how you do on these two. Pause the video now. Okay, and then finally, here you're going to be using sort of some techniques that are similar to when we derived the 2 formulae. You know, where you draw the graph and then use a bit of geometry to equate things. See how you do. That tip there on the right probably does make sense. Best to draw or quickly sketch up, it doesn't have to be perfectly precise, a velocity time graph. Try that question. You can pause the video now.